Welcome to the screencast introducing the logistic function. In our studies of exponential functions, we have seen that if we assume that a population grows at a rate that is proportionate to the size of the population, it follows that the population grows exponentially according to the model f of t equals ae raised to the kt, where a is the initial population and k is tied to the rate at which the population grows. Since k is positive, we know that e raised to the kt is an always increasing, always concave up function that grows without bound. While f of t equals ae raised to the kt may be a reasonable model for how a population grows when it is relatively small, because the function grows without bound as time increases, it cannot be a realistic long-term representation of what happens in reality. Indeed, whether it's the number of fish who can survive in a lake, the number of cells in a petri dish, or the number of human beings on Earth, the size of the surroundings and the limitations of resources will keep the population from being able to grow without bound. In light of these observations, a different model is needed for population, one that grows exponentially at first but levels off later. Calculus can be used to develop such a model, and the resulting function is usually called the logistic function. A logistic function has the form p of t equals a divided by the quantity 1 plus me raised to the negative kt, where a, m, and k are positive constants. Notice, the graph of the logistic function is always increasing, changes from concave up to concave down, and p tends toward a specific value as t increases without bound. We call the value to which p tends toward the carrying capacity of the function. In order to use the logistic function, we need to consider how the values of a and m relate to the carrying capacity and the initial value of the function p. So first, let's see how the carrying capacity a relates to the values of a and n. In a previous video, we saw that since k is positive, it follows that e raised to the negative kt tends towards 0 as t increases without bound. That means the quantity 1 plus m times e raised to the negative kt tends toward 1 plus m times 0, which equals 1, as t increases without bound. So in other words, the denominator of p is approaching 1 as time goes on. And so we can say that p of t tends to a divided by 1, which is just a. So p of t tends to a as t increases without bound. And that's why we can refer to a as the carrying capacity of the population. Next, we want to understand how the initial population relates to the values of a and m. We can represent the initial value as p of 0, and evaluating the function at t equals 0 results in a divided by 1 plus me raised to the negative k times 0, and that simplifies to equal a divided by 1 plus m. So the initial value, p of 0, equals a divided by 1 plus m. And solving for m, we'd multiply both sides by 1 plus m to get 1 plus m times p of 0 equals a. And dividing by p of 0 on both sides results in 1 plus m equals a divided by p of 0. And then subtracting 1, we find out that m equals a, the carrying capacity, divided by p of 0, the initial population, minus 1. So once we know the values of a and m, we can use a non-zero value of t to find the value of k. In a subsequent video, we will practice finding the values of a, m, and k to model a population's growth using the logistic function.